Alrighty, folks, good afternoon. Welcome for those who are joining us for the first time, and for those of you who are joining us as a repeat, welcome back. We are getting started today with our fourth session of the Municipal Education Series on microgrids. My name is Rachel. I am a program consultant with Geo. Before I turn this over to Michael, as always, I have just a couple of housekeeping items to keep us organized. So first and foremost, as always, this session is being recorded. It will be posted to the Geo YouTube channel later this week. We ask that everybody please keep their cameras and microphones off for the duration of the presentation, so that we can focus on our speakers and their presentations. Michael and our speakers will be doing a Q&A at the end of the session, but if you have any burning questions that you want to put in the chat, feel free to do so. We will be answering all questions at the end. And then if you're having any technical difficulties, I will post my email in the chat. Feel free to shoot me an email. I've got it up in the background here. And I'll try to help you as best as I can. But before I turn this over to Michael, if everybody could just post where they are located in Ohio, we'd love to see what the geographic representation is in the chat here. Go ahead and post that. And Michael, I will turn this over to you.
Well, thank you, Rachel, and good afternoon, everyone, for session 4 of our microgrid education series. This will be the development process for those of you who want to figure out how we go from do I want a microgrid? What the heck is that? And to actually designing and building one, you are in the right place. So we are going to go through with two excellent speakers on the kind of ideas you need to have in your head to get started. So, number one, you need to work with someone who knows what they're doing. This really is technical type stuff. You're going to need to have some help with that. You also need to make sure that the folks you're working with understand you and your unique use cases. This is a municipal education series. So, because it's municipal, you have special roles, mission critical responsibilities for the safety, health, and well-being of every resident, business, and visitor of your community. So because of that, the type of system that you are going to design needs to be very specific. And the process to get you there also needs to make sure that you can clear the high bar of taking care of the safety, health, and well-being of every resident and visitor and business in your community. So do not do shortcuts. Watch out for cookie cutter solutions. They are not your friend. You need to make sure that what you are getting exactly is what you need. So how do we do that? We go through the process with people who really know what they're talking about. So, on my apologies, I was supposed to talk on this slide. So, very quickly, think about what you want, figure out what you're using currently, figure out what you're going to have, go ahead and get it built, test it out to make sure it works properly and safely and reliability. Then, when you go to operate it, you get to optimize it. And by the way, my clothes dryer electric is running on sunshine right now. It's just my favorite thing. I'm in the middle of February and I'm producing enough energy to literally just run my electric dryer and I'm not using anything off the grid. It's pretty cool stuff. Once you start doing those kinds of things with your microgrids, you're just going to be amazed at the kind of fun things you could do. So the folks who are going to tell you really all about this process. Amy Simpkins, welcome back. She was on our session 3. She's on our session 4. We get to leave her alone after this one. She's the co-founder and CEO at Mugrid Analytics. Amy Simpkins architects reliable, adaptive command and control for mission-critical distributed energy systems. Mugrid provides bankable techno-economic analysis, which I don't know what that means, but she'll tell us. Optimize control and project development of renewable energy, energy storage, and microgrids to maximize economic return, increase energy resilience, and promote energy equity in the U.S. and around the world. She's also the author of Spiral, a catalyst for innovation and expansion, and holds a master's degree in astronautical engineering from the University of Southern California and a bachelor's in aeronautics and astronautics from MIT. And yes, she was a rocket scientist, an honest to God rocket scientist. Also with us, Peter Worley is just as good as Amy, very intelligent. He co-leads Go Sustainable Energy's Distributed Energy Resources team, which this is a distributed energy resource microgrids. They help clients to navigate the complex world of grid interactive technologies such as renewable energy, demand response, microgrids, and energy storage for both on and off-site opportunities. Leveraging his knowledge of product design and design innovation, he helps clients develop frameworks, strategic plans. Peter works with municipal utilities, including some of the largest in Ohio, and is Go's client lead for the Cuyahoga Green Energy and Westerville Electric Division. So if you are up in Cuyahoga County, which is the only microgrid utility in the state, Go Sustainable Energy is one of their folks. Peter's background is interdisciplinary with a master's degree in energy and resources from UC Berkeley and a bachelor's degree in mechanical engineering from the Ohio State University. His master's thesis analyzed the economics of Ohio industrial electricity rates. He enjoys the outdoors, backpacking, the indoors, a book club, doing indoor things outdoors like board games, and doing outdoor things indoors like gardening. He usually uses his indoor voice, and in the Columbus community, he supports I Know I Can, the Ohio Energy Project, and the Washington Gladden Social Justice Park. So welcome to Amy and Peter. And the good thing is I get to step aside and let them go. And the first one off the bat is Peter. So thank you very much.
Thanks, Michael. Yeah, not being a rocket scientist, I need a longer bio to pad mine compared to Amy. So thanks for that introduction. Um, so yeah, I'll get things started, and you'll see here the high level of the development process for microgrid. You'll see 6 steps here. Um, Other folks might present it in 5 or 4, but at least we show you the beginning, which is feasibility assessment, and the end, which is operations optimization. I'll be speaking about the first two, feasibility assessment, cost estimation, and financing, and then Amy will talk through the last 4. So, Michael, if you get us started, we can step into the next slide. So to give you all a little bit more background, so I've been with Go for about 8 years. And we've been working with microgrids. We are an engineering consulting company. So we don't design or engineer solar or batteries. We don't construct it. We don't operate them. We are purely consultants offering accurate and biased information. So we come in that first 2 steps. And then there's other groups who will go steps 1 through 6 or steps 3 through 6. But just know that we work in the steps 1 and 2. That's why I'm talking about them. And Amy's going to help talk about the other ones. So some of the experience that we've had with microgrids is we helped do a feasibility assessment with the City of Columbus, who's looking at doing a microgrid at their booster station, which is this photo here. So the solar and battery system can help them if there's ever a power outage. You know, water towers have storage of water, but slowly that water comes down, and then you need to pump it back up. They had diesel generators that would get rotated to different sites, but they thought, hey, that'd be a real nice avoid of a headache if you didn't have to coordinate that diesel engine coming around to their site. Instead, they could have solar and batteries to help pump the water. Another project we've worked on with the City of Columbus is help them with the microgrid prioritization study. So they have a climate action plan goal to have 5 microgrid pilot projects by 2030. So they want to help thinking about where to put them and what technologies to use with them. Do you do it at a traffic light, at a busy intersection? Do you do it at a urgent care? Where are good spots around the city to pilot microgrids? And then Michael mentioned earlier about Cuyahoga Green Energy. So we are still working with Cuyahoga County as they create their own municipal utility from scratch that's focused on microgrids. So they want to not just have one building have backup power and be a microgrid. They're hoping to have an entire district. So 6 manufacturers, an industrial corridor, and say 5 to 10 municipal buildings with the City of Euclid, City Hall, High School, all be able to be powered with a microgrid if there's ever a major transmission outage. Some other projects we've worked on is with the state agency Drive Ohio, who's helping administer federal funds for EV chargers. They were curious about microgrids and those being able to support EV charging. And we also have a good amount of folks on our team who work at hospital systems throughout Ohio as energy managers, and so they have to be aware of those backup power systems or microgrids at a hospital. All right, next slide, please, Michael. So the feasibility assessment is the first step, and just to help you all kind of recognize roles in this step, being city officials, is this step, the responsible party is the consultant you hire to help, and that you will be part of the process, but you're there to help provide information, provide constraints you have, and so you're in a consulted role. And then the goals of this step is really to lay down a foundation for the next 5 steps. So getting information to help you realize what's the size of system you want, what's the operation strategy for it, where the economics going to be, and the financing. And so some of the main tasks of a feasibility assessment is going over the goals, understanding the economics, the regulations, understanding utility contracts, and the site conditions. And so the risks of skipping this step is you might end up building a project, a microgrid that's too big or too small, which means you might be overpaying for something. It also might mean that you wanted to have a microgrid for a library and now it can only run for 3 hours instead of you were hoping it could run for 16 hours. Also, there's chances that you have some contracts with energy suppliers that you didn't realize you had, and you could face some issues with getting off of those. And then again, if you don't lay a strong foundation, there's a chance you could be misspending time where you get a lot of questions from vendors or from the operators about the microgrid because you don't have a foundation laid down to help answer those. And then to give a sense of timeline for this step, this is really high ballpark. Things can happen quicker, but we give a sense of 6 to 12 months. If it's a smaller project and you kind of already know exactly what you want, that can be much, much shorter than that. But if it's going to be a big project, maybe multiple buildings, and you don't exactly know what your main goals are, it could take longer. All right, so the process within step one that we often take is first is to engage stakeholders, and we'll go into a little bit more detail about that in the next slide. The second step is analyzing your existing utility costs. So electricity costs are more complicated than gasoline. Gasoline, you go to the pump, costs you $3 a gallon. You maybe look at your electric bill, and it looks like it says 10 cents a kilowatt hour is everything all in. If you take your total number, divide it by all your electricity. Well, unfortunately, electricity is a bit more complicated with that. And so it's important to understand all the different components and how they're charged. So that pie chart there kind of starts showing you the complexities of what's in an electric bill and how a microgrid might affect those different components differently. The third step is providing a site and regulatory review, understanding what kind of technologies you could use at your site and regulations you have to stay within. And then the fourth step and final is sizing the system. So I'm going to take this next slide. We'll talk a little bit more in detail about engaging stakeholders. So this is a really important step, lays down the foundation for the foundation. So this is a moment as a city where you bring in maybe folks from your finance department, real estate department, your business continuity staff. This is a moment to understand everyone's goals and also understand prioritizing them because some of these goals could be in tension with each other. But some of the main goals that we hear from our clients are maybe the sustainability department has a renewable energy goal to have more renewable energy. Maybe the facilities department is trying to reduce the utility costs. Maybe you have folks where you have equity goals where there's people and communities without a lot of air conditioning, so you want to have cooling centers and have a microgrid to power that during a hot summer outage. That relates to another bullet in there you see on health. Again, microgrids can help with health, with heat exhaustion. And then there might be business continuity. So if you have requirements to keep buses running, to keep services going during outages as a city, that might be a chief aim as well. A lot of these kind of get boiled into two main buckets, reliability and resiliency. Microgrids, if I simplify them, it's like, hey, you want backup power. Well, what kind of backup power? And there's two kind of main camps. Again, these terms aren't industry standard, so you'll hear people use them interchangeably, but for today and for this framework, we'll use these two definitions. Reliability are the ones that are shorter duration, but they happen more often. So this is like the ones that we all experience probably a couple times a year. The power goes out for a few minutes, goes out for a couple hours, comes back on. We know they're probably going to happen, but they don't last too long. So reliability is, you want to avoid those. Resiliency is ones where your power goes out for a long time, but doesn't happen too often. So that's like maybe City of Columbus a few years ago in the summer, there was a major outage on the east side where power is out for days on end. So these are happens less often, but when they do, they last longer. All right, Michael, next slide, please. So when you start getting a sense of a microgrid and what you're looking for, what's reliability or resiliency, um, this will help start you being able to answer the sizing the system question, because that really starts helping to figure out how big of a system you need. In short, if you're looking for reliability, you need a smaller system. If you're looking for resiliency, you're going to need a bigger system. But going in deeper, um, there's a balancing act with electricity. And it sounds like an earlier part of the series that talked about how, with a building that's connected to the electric grid, anytime you turn on your air conditioning or light, the grid immediately matches your demand with supply instantaneously. And so if there's a power outage and your building no longer has access to the grid, your microgrid now has to do that instantaneous matching of electricity supply with electricity demand. So on the top part of the equation, for demand, things that go into determining the demand for electricity is first, what's your current electricity load? You have air conditioning, you have lighting at your building, maybe some computer servers. Then the next step is there a plan to have more electricity at this building? Maybe you plan to have EV chargers, or you're going to electrify your space heating. Then there's another component to realize is, are you going to be doing some energy efficiency at the building? Can that reduce the amount of electricity demand you have? Often this is a helpful step where putting in LED lights or more efficient air conditioning is a lot cheaper than building a bigger battery or a bigger solar panel. So that's kind of your demand side. And then on the supply side, this is where you start thinking through how do you match these three components in the most economic way? If you got generation like solar or fuel cells or natural gas engines, you got storage like batteries, and you also have load controls. So again, if you're looking for a microgrid at City Hall, and if you can set back your thermostat, say from 70 degrees to 74 degrees in the summer when there's an outage with load controls, then maybe you don't need to have as many solar panels or as many batteries to last as long. So this is what gets into kind of a fun engineering calculation, is figuring out the right mix of those three technologies. And those technologies are really dependent on your goals. Um, what we see often with cities is with microgrids, they can be a climate solution, but often it's, are you looking for a climate adaptation or climate mitigation? So we're experiencing climate change, more extreme weather and hotter summers. You might look at a microgrid as to solve adaptation, to have cooling centers. And a city might decide, all right, how much do I want to do microgrids for that? Where am I willing to spend money to do natural gas engines to have longer lasting microgrids? But that comes at a cost of you have emissions. And that's your other part of climate, which is climate mitigation, which is reducing emissions. And so that might then decide if you're focused on that goal of climate solution, then you're not going to consider natural gas engines. Maybe you just focus on solar and batteries. So these are the things that kind of helpful. This feasibility assessment is really understanding the goals of the microgrid, and that in fact decides the different generation and storage technologies. All right. So once you have a general sense of the size of the system, you can go into cost estimation and financing. When doing these analyses, kind of create two scenarios. One is the business as usual scenario. So that's the stuff on the side on the left. Feasibility assessment helps understand what's your current utility costs for electricity and natural gas, how much you're currently spending, and then also get a sense of your disruption costs. So these are often a little bit more qualitative, but I think most buildings and companies and cities can understand when the power goes out, there's a lot of headaches. There's also maybe a lot of backlog of work, and that has a cost to it. And sometimes it can be even more quantitative in that sometimes power outages damage equipment like motors, and so you have to replace that, and that's a cost. Or you have to send staff home and pay them without they'd be doing work that day. So that's the business as usual scenario. And the scenario on the right is the microgrid scenario. So now what's the world like with the microgrid at your building? First, you determine how much the utility costs are. And you see that blue bar is a little bit smaller than the one on the left because often a microgrid can help reduce your utility costs because you have solar and batteries, and now you don't have to buy so much from the utility. And so it's important to know how much those utility costs can decrease with the microgrid. And then you see under disruption costs, it's hollow because hopefully at this point now, with the microgrid, you can avoid those disruptions and those headaches. And though to get those disruption costs avoided, you need to pay for microgrids. So the microgrid cost is its own blue bar. Um, and there comes to be a point where you're kind of comparing your blue bars on the right to your blue bars on the left. Um, can you get a microgrid that can avoid disruptions at a cost that is similar to what you're currently experiencing? Sometimes that's pretty hard to do, um, but often people might be willing to pay a little bit more to have power that's greener and more reliable and more resilient. And that's kind of that last bar of achieve goals in green. That's like a benefit that you might be helping achieve your climate action plan goals or some of your mayor's goals, having more renewable energy, and that's worth it to maybe have a slight price premium. But you hope and see if you might be able to do it all without increasing costs too much. So once you get to this point with cost estimation and financing, we have a sense of is it worthwhile? That's kind of this last step. Will it be worthwhile to you as a city to do this? Then you can start thinking through how to finance it, whether you do it with your own money, with a cash project, or if you get a loan. But if maybe you've used up most of your debt capabilities for the year, you can then go to a third option, which is you can have someone finance it, and then you pay them back through a monthly payment. Sometimes it's called a microgrid service agreement or power purchase agreement. But this first step of the economics helps you decide whether it's worthwhile to do it. And that's kind of a go, no go point of do you do an RFQ or an RFP to now hire a vendor to do the engineering, the procurement, construction, operation of the microgrid? And before I hand that over to Amy, I'll just do one last point, which is for those people in cities that have municipal utilities, this is a particularly special opportunity to work with them. Investor-owned utilities can be more of a difficult to maybe work with, or they have more specific rules on what your interconnection can be like. They have very specific rules on what you have to pay. But if you have a municipal utility, you can be collaborative with them about the rate design, and you can be collaborative with them about maybe what parameters you have to stay within. So I'll just flag that as a great opportunity for those cities with municipal utilities. All right, so with that, we'll pass it on to Amy to talk about steps 3 through 6 once you, as a city, have hired a vendor to help with the last few parts.
Thanks, Peter. So, Michael mentioned during my intro that I am a rocket scientist. I spent the first 10 years of my career in spacecraft engineering. So we're going to talk about space actually for a minute. Um, and we'll come back to microgrids. I promise that it relates. In 1962, 6 months after John Glenn orbited the Earth 3 times, John F. Kennedy made his famous speech from Rice University that we were going to go land a man on the moon within the decade. And everyone is very inspired by this. You know, regular, normal people very inspired by this. But if you think about it from the engineering perspective, and with you all being, you know, from municipalities, you can imagine how this went, right? The president or a staffer of the president called somebody up at NASA and was like, hey, do you think it's possible that we could go to the moon in a decade, by the end of the decade? And that person at NASA was like, well, hypothetically, given enough money, like, sure, hypothetically we could. And then there's the president talking about that we're gonna do it. Fast forward, of course, and it actually happened. We actually did it in 1969, July 20th. Americans walked on the moon for the first time, and then several times thereafter. But what happened to go from someone at NASA saying, hey, hypothetically we could do it, to no kidding, there are footprints on the moon. So I'm calling step 3, the step into systems engineering. Stuff gets real here. So you've seen, Peter did a great job going over the very, very important feasibility process of having the idea to incorporate distributed energy to build a microgrid and really wrapping your minds around and the minds of your leadership and your communities around what that means and what goals can be achieved by doing that. That's an incredibly important first step. And you'll get a lot of people, and I'm calling out especially Michael Benson because he's my friend, but you'll get a lot of people who do that work where you say, would it be possible for us to incorporate this technology, or would it be possible to get this functionality with our microgrid? And the people who do the feasibility studies, like Michael and maybe Peter, I just met Peter, so I won't call you out, but they'll say, yeah, that should be totally possible. And we love that. We love the optimism. But now the rubber meets road, right? You have gotten financing, which is going to be covered in the next municipal session. And you are, like Peter said, you're starting to hire vendors and laborers to do this. And so how do we move from the idea of what the thing could hypothetically be to what it is and make sure that it works in a way to meet your goals? And the discipline of systems engineering was invented to do this. It's a little bit different than mechanical engineering or electrical engineering, which is very specific about those types of technologies. And systems is more like, how do you get everything to work together to make sure that you're achieving your goals? Now, many people who think about distributed energy will think about it as an extension of the building or an extension of the facility. And in building construction is pretty well understood, right? You have a lot of common parts and you have a lot of systems, electrical, plumbing, structural, that all have very well developed standards, very well developed standards of practice in the engineering, and all buildings serve approximately the same function. Some of them are a little bit more specialized than others, but they all are approximately the same. And so you don't really need to spend a lot of time on how does the whole system come together when it comes to a building, because we know that. We've done it thousands of times, millions of times as an industry. Spacecraft are the other end of that spectrum. Spacecraft are completely bespoke almost all the time. And a lot of times we're bringing in new components and then trying to get to fit the new components together in new ways to create something entirely new. Microgrids and distributed energy fall in between those two extremes of the spectrum. They're not quite as bespoke as a spacecraft, but also they're not quite as standardized as buildings. And that's when I'm talking to a group of folks that is really familiar with how building development works and like what it's like to construct a new building. It's important to say, hey, this is actually a little bit different. And I don't say that to scare you off, to say that it's more complex, it's more innovative, it's more risky. I don't say it to scare you off. I do it to set expectation and say, this is what you should expect. You should expect there to be some innovation, some curiosity, some creative thinking, and you should expect it to be maybe a little bit slower than you would normally think of for a building. Next slide, please. So how do you think like systems engineer? Like I said, it's a little bit of a different discipline from some of the traditional engineering. Systems engineers like to define the problem before they solve it. That's what we did in the feasibility stage with Peter. Clarify the interfaces between different components that make up the system, identify the constraints, model the interaction between those components and between the system and the outside world, test our assumptions, that's a big one, and design for the entire life cycle of the project, not just how do we get this built fastest, cheapest, etc. And the testing part is a really important part. If you think of a building, you don't do a lot of testing, right? The building, when you construct the building just is. And yes, I can walk in the door and the door shuts. Great, test over. What is there to test, right? But in these systems where there's complex software and hardware interactions, the test part is really important and sometimes gets overlooked because if we look at the distributed energy system, like just an extension of the building. Over here on the right, we have a pretty standard generic, it's called the V chart from systems engineering. And this talks about once you've done your project planning, once you've done your project feasibility, you should want to then develop some things, a concept of operations, some requirements, and not just jump straight into design. When we talk about a building, which is a well understood system, oftentimes we're skipping straight from the project planning into the design because we're like, yeah, I know how this goes. I know what you want. Now I know how to put it together. Because we know inherently, intuitively as a human, how the concept of operations for a building goes. It's not that complicated. And so what I want to impress, and same thing on the other side of the V, we're often going straight from the implementation part, the build part, straight to deployment and acceptance without that verification, which is the testing part I talked about. And I've seen it more often than makes me comfortable is that there are some folks out there that are skipping these steps in a systems engineering process for microgrids, for distributed energy, and that's causing some projects to not meet their goals, like we just defined in the feasibility study. So I'm letting you know that like you should want to see these steps in your process. And if the folks that you're working with aren't digging down into these steps, you should be asking questions, asking detailed questions about these things. So next slide, please. So we're not going to go through every single bit of this. And some distributed energy systems are, especially as they get larger and they have more different types of assets. You saw that in Peter's presentation. And if you were with us last time, we talked about that. The more different assets, the larger they are, the more complex your system, and therefore the more systems engineering you should want to do to make sure that everything is going to work together to achieve your goals. I've listed a few different tools. And so if you have a small system that's fairly basic and straightforward, you might do less of this, but you still want to do some of it. So you should be talking to your design folks about the concept of operations. How is it going to work? In what order? We saw in the feasibility study, we talked about providing reliability, providing resilience. And yes, microgrids can do all those things. And now as we're entering into design, we ask, how will it? And how will these components work together in order to provide them? And the answer is in the concept of operations. What is the sequence of what happens? What is the function of each individual piece? And we also want to see not just the electrical flow, how is the electricity going to flow through the system, but how do the different elements of the system communicate with each other so that the right hand knows what the left hand is doing. That communication rolls into dispatching models. That's the system deciding when and how to use its resources. Risk management is something that not a lot of people like to talk about because it's like the bad things. What bad things could happen? What are the failure modes? If something does go wrong and there is a fault in the system, who's in charge of fixing it? Sometimes it's as easy as unplugging the inverter and plugging it back in. These are not like catastrophic failures, but these systems do need someone to pay attention to them. So we talk about risk. Requirements definition is a really important part. We just set in the feasibility stage all of these beautiful goals, and we drilled down into how much it's going to cost to achieve the goals and done the cost benefit analysis. And the requirements are where those goals are translated into technical requirements so that the technical system that gets built actually achieves the goals. I already talked a little bit about verification and test. We're going to talk about it more in a minute. One of my big things here is the system acceptance testing, making sure that the system works the way you thought it did in that concept of operations. And then performance validation. You would be surprised how many people put in distributed energy of any kind, and that could just mean a few solar panels. And then they really don't go back and look, and they were probably sold the solar system on how much money they were going to make or save on their utility bills. And they did this cool calculation of what that would be. And then no one ever goes back to recalculate and say, what actually was it? What actually would it have been? And so this performance validation is also near and dear to my heart. I want to see sites see the benefits. And then tying it all together is system architecture. And that's what you see at the bottom, is that how do we take all of this work about fault detection, this work about sequencing, this work about test planning, and how do we take that and translate it into a technical design that brings it all together and enables the performance? That's what system architecture is. So next slide, we'll talk about design maturity. Oh, go back one. Yep. Design maturity. So the microgrid design is an iterative process. If you took away nothing else, take away that you're going to see several versions of the design before you're ready to finalize. And one thing I wanted to add to Peter's presentation about doing the feasibility study, doing that cost benefit analysis, things are a lot cheaper to change or fix in the feasibility stage, where it's all on paper, it's all in thought space. And once we start actually purchasing equipment, once we start hiring people to do the actual design, and then of course when construction starts, things get way more expensive to change. So that more expensive to change increases at each stage of the design maturity, which is why we take these times to go back and validate the design each time and make sure we're ready. So the 30%, okay, a word on these percentages. These are the percentages that I use at my company, Microgrid, and we use with our clients. They tend to be fairly, I won't say standard, that's not even a good word. They tend to be used also like around the Department of Energy, because we do a lot of work at the federal level of the Department of Energy. So you'll see this like 30, 60, 90, 100 flow. But your contractor might use different. I have one project right now that really, really wants to talk about the 45% design. And it doesn't really matter. Those numbers, the numbers themselves don't matter. These are the stage gates in design maturity. So at 30% design, this should be the output of the feasibility study that Peter did. Okay. We've got conceptual sizes for the major components, whether that's solar, battery storage, natural gas generator, wind, whatever you've got. And then the basic operational concept and dispatch strategy. The basic operational concept is how you determine what that cost benefit, especially the benefit side of that cost benefit analysis was in the feasibility study. And you've got the big driving requirements because you set your goals, right? And you probably have a single line diagram of the system. That's where you show like a box for the solar, and it's connected by one line to the box for the battery, and then connected to a box for the building. That's a single line diagram. Okay, so now you're ready at that point to talk about financing. Again, that's next time's topic. And you're ready to start more serious design of the stuff getting real. How is this going to work? How are we going to build it? How's it going to come together? So moving from 30 to 60% design, we're going to now, instead of just a conceptual size of your major components, we're going to talk about makes and models of batteries, generators, solar panels, etc. We're going to drive down into a very detailed concept of operations, because a detailed concept of operations tells us what other pieces of the system we might need in terms of switch gears and relays and circuit breakers and that sort of thing. We're going to start to talk about the siting and the layout at your facility, because we want to make sure that, like, if we're doing some ground mount, there's no environmental considerations or wetlands. We want to see how your building is paneled to make sure that we have the right panel configuration on the microgrid. And the output of the 60% design level and the single line diagrams that come and layouts that come out of that are usually sufficient for the interconnection application. And most interconnection applications with your utility are going to ask these questions. What are your major component makes and models and sizes? How is it they have a few questions about the operation, about when it's going to charge from the grid or when it's going to export to the grid. And then you're asked to submit these preliminary design documents. Okay. Then there's at the 90% design level, it starts getting really real, because we're going to spend some money now. We're going to go out for procurement. We're going to buy those solar modules. We're going to buy a battery. We're spending a lot of money here. And that's why we're really close to full design maturity. And we have a full drawing set. We're ready to submit for construction permits with the AHJ. We're ready to program controls, because we know most of what's happening with the system. The things that might change between a 90% design and 100% design are often kind of the ancillary details that an installer contractor will bring in. This brand of circuit breaker wasn't available, so they switched it out to this brand. They're usually smaller, non-major components. They're usually availability driven, but they're usually pretty readily available off the shelf items. And yeah, so the final stage here is 100% design. It depends who you're working with. 100% design might be ready for construction, or it actually may end up being the as-built set, reflecting ultimate reality. Sometimes there's a 100% and then there's also an as-built. Sometimes they're the same set. But basically, this is what goes on file with the utility as what the system is that is interconnecting. This goes on file with any AHJs that need to see the system, and it informs all of the system acceptance and commissioning that goes on. Next slide. All right, so next we do procurement and construction. And I say it with a little bit of tongue in my cheek that this is the easy part. Now, Michael can go, and the Green Energy Ohio folks can go out and get an installer to come tell you about all the details about why construction is hard. But in my mind, we've already made all the hard decisions, because we've already made the dollar commitment. By purchasing equipment, we know what we're doing, and we're ready to do it. So let's do it. So this is just a variety of cool pictures I have from projects that I have worked on about installing and programming and site prepping a variety of projects. In these pictures, you'll see some trenching, you'll see some utility style relays, some batteries, and some solar panels. But please take that with the winky face emoji that I have given you, that I understand that, just someone who does this for a living, this is not necessarily the easy part. That's just me. Okay, next slide. Okay, so now everything's installed, and now we talk about commissioning. System commissioning is the milestone that you will hear, that it means the system is ready to work for you. Everything is done. The installers and the construction is going to go away, and the thing will work now. And my first question for you here is, you wrote an acceptance test plan, right? We'll come back to that in a minute. Of course, you will want to perform the necessary inspections. And yes, I saw in the chat, thank you, someone defined my acronym. AHJ stands for authority having jurisdiction, which means whoever is in charge of issuing electrical and construction permits. It's probably the county. There could be state permits. There could also be city permits, depending on what you're, and obviously, like Peter said, as a municipality, you can work in conjunction with the AHJs on the project. So hopefully it goes smoother than normal to do the permitting and then the inspection process to validate the permitting, right? The utility to perform full interconnection will need to do two things. One, they will review all of your inspection reports to make sure that the AHJs have signed off on the project. And then they will conduct what's called a witness test, which basically operates the systems in various modes. And it makes sure that it's not going to put energy back onto the grid when they don't want it. The reason for that is if there was a grid, like for example, in a resilient situation, what you'll often have is you'll have a recloser or a switch that when it detects that the grid is out, it opens. So and by a switch opening, no electricity can flow, right? It's off. And then your microgrid can start up and run your site by itself. What the utility wants to make sure of is that while your site is running, it is completely disconnected from their system so that you couldn't accidentally put power back on the grid, because since they're having an outage, they're going to have linemen out working. And if you were to accidentally send voltage and current down that line while there's a lineman working on a problem, you could hurt that person. And no one wants that. And so they're making sure that the switch stays open until you say it should close, and that they don't see any energy coming back onto the site. The final thing here is you'll get from the utility who has validated your inspection permission to operate. And that document, that sign off, that's the official moment when you have a microgrid and it is working for you. But here's the thing, utility and AHJ approval just means your microgrid is safe for the building and for the utility system, the grid system. It doesn't necessarily mean that your microgrid works in the way that you thought it would, that it's going to reduce your utility bills, that it's going to provide resilient backup power when it's time. And so that's why you write an acceptance test plan. And by you, I don't mean you, I mean your contractor, but you should ask for one. What is the acceptance test plan to make sure that the microgrid is going to do what we think it's going to do? Next slide. Then we move, once that happens and we've commissioned the system, we move into operations and maintenance. Some people out there like to say that these are maintenance-free systems. And sure, compared to a generator, which you might have to run once a week to cycle the oil and the diesel and et cetera, these are pretty low maintenance. However, they are not maintenance-free. You need to pay attention. Sometimes they're computer devices, so sometimes they stop working and the inverter stops working. And like I said, you just reboot it and it starts working again. But someone needs to notice that that is happening. And so we want to make sure that your system is performing economically. So we want to see some monthly bill validation against your utility bill. We want to see maybe quarterly and annual reporting, like how are we doing overall? Because your utility bill savings is probably going to fluctuate depending on if it's winter or summer, seasonally. You'll see a lot of folks offering system health and status monitoring for functionality. This is things like the state of charge of the battery and the temperature of the battery, which is really important for the system, but it doesn't necessarily tell you about what it ultimately is doing in terms of delivering economics and resilience. And so if your system is performing, you don't really have to worry about that. It's more that if it's not performing, engineers can look at that health and status information and say, this is why. This is why there's a problem. Islanding, when we have those big black swan event outages that Peter was talking about, is not a very statistically relevant event, right? These don't happen very often. And so often when you talk about is it performing in these resilience cases, we're talking about individual case studies. So it's important to document what happened, what caused the outage, how long did the outage last, and how did we do? And were there any variances of note that we need to work on with our providers, whether that's a monitoring company or a maintenance company or your consultant? We already talked a little bit about fault detection and response. You'll want to know who's on call, who gets the notification. And then if something is really wrong, more than we just need to unplug it and plug it back in, who should you call? Do you know? Is it someone at the vendor? Is it someone at the installer? And who has access to the data? Preventative maintenance takes a variety of forms. Sometimes it comes with your warranty. Sometimes your installer will include a package, a maintenance package for you. And there are a variety. You don't have to have a maintenance package at all and just, call by the drink when you need help. There are a variety of ways to do it. And so it's just knowing what the terms are and knowing when to call. Next step. This is one final thing to say about operational control is that selecting the controller, when we talked about selecting the controller back in at the last, when we talked about components, but we want to make sure that the controller is properly programmed and has the dispatch strategy that you assumed it would have during the feasibility stage. We have seen controllers out there that are literally just a piece of software that has functions, but it's up to you or someone else around you to say when those functions get used. So make sure that you are insisting on intelligent control that is set up prior to commissioning. Make sure you are going back and looking at the data and saying, how is this actually working? And is it delivering the results? And are we achieving the goals that we set at the beginning of this project? Next slide, which is our get off the stage slide. Thank you so much for your time today, and happy to take questions, but I'll turn it back over to Michael.
We are pressed for time, and I don't see any questions yet in the chat, but I do have one of the comments I was going to ask you guys. How are you using what they call digital twins? And for those who don't understand, it means you can actually make a computer version of the system that you've designed and operated on the computer before you actually operate it in the real world, and or operate the digital twin with the problem you're having in the real world to try to figure out what's going on. Are you guys using digital twins in your processes?
I'll let Amy go after me because mine's short, which is I don't use digital twins. Our level of analysis is higher level and simpler. So we do our modeling in an Excel spreadsheet. You got about this big of a solar panel, this much amount battery, do some high level assumptions. So digital twins are maybe a more in Amy's world and later in the design stages.
So yes, we absolutely do use digital twins. If you go back up to the previous slide, the control system that I have here, Red Cloud, is the control system that my company sells, and we absolutely use digital twins, where we have a software simulation of what we think it should be doing alongside what it's actually doing. And we use that digital twin to predict performance. It's how we understand that we've got the right dispatch strategy. But then, of course, real-time performance sometimes differs from that digital twin because maybe the sun went behind a cloud. and we didn't realize it. And so it really does give us a high level of detail about how the system is performing, how it's adapting, and if it needs human intervention to do better.
I see Frederick Stockwell unmuted. Frederick, do you have a question you want to use verbally?
No, thank you.
No. If no one else is going to ask, then I'm going to mention something. When we go to session 6, the final session, Amy mentioned black swan events because this is a municipal microgrid education series. That's one of the things you actually design for. Rather than something you deal with when it shows up, it's something you might actually design for. You need to look at, did your community have a major, let's say you're Xenia, Ohio. Did you get hit by a tornado? How long were you out? How did you get your services to operate and have a microgrid to help provide that resiliency? You might design that tornado proof, hurricane proof, which there is no such thing, but at least harden your infrastructure along with your microgrid to be able to operate your system. And we are going to get an education and an example out of Western North Carolina on session 6 about their black swan event, their hurricane that they had to deal with, and how microgrids are a key component to their resiliency for that area in Western North Carolina. I'm shocked there are no questions. I got one more comment before we'll finish off then. Those of us who are from municipalities, you test your tornado sirens if you have them every March. Your schools do a tornado drill. You will do a drill every March. Amy made me think of this. When you have a microgrid, you probably ought to practice everything went to heck in a handbasket and shut down, and let's make sure the microgrid does what it does. You should practice black swan events. If you are a municipality, you do that. You drill. You either do a tabletop drills, you do full scale drills, you do small individual component drills, but you practice for the worst days. And your systems are going to be designed to operate for your worst days. So you are actually going to be your microgrids will be fun to function with and make them go and see what they do for you during those kind of situations, because it is not new technology, but it is a novel new application of this technology to municipalities, which we will also discuss in session 6. We have just 3 minutes left. I see no questions in the chat. Am I missing anything, Rachel?
I'll just add on to that, Michael, and say that I believe that humans in general are really bad about practicing for black swan events.
Yes.
We don't like to think about the things that go wrong, and that's why we get caught unawares and we have trouble responding to emergency events like flooding. I mean, the flooding in northeastern Ohio a couple of summers ago, where we got 7 inches in 1 hour. It was
Yeah, it's crazy.
insane,
Yeah.
and biblical, right? And but and so I do think it's important, especially if your distributed energy systems are part of your resilience plan, getting emergency management involved. Like, how does your municipality typically manage emergencies? How do you typically prepare and practice, including running your sirens? Because we have projects at courthouses and jails and wastewater treatment plants, and it's hard to practice those things when there's day-to-day business to be done. But it is really important, listen to your emergency managers and how they handle these situations, and make it part of the regular plan.
Okay, we got 2 questions came in and we are down to like 60 seconds. So, Miguel, your data is your data. You absolutely will be able to log and go back and see, because that's how you analyze and figure out what happened, but it'll also be your data. It may not be something that's out in the cloud. If it is out in the cloud, it's under your services and controls to make sure it's safe. Leslie, absolutely not. There is no like simple answer. Every one of them is unique and different, because what you use at your recreation center and what does a mid-size mean? You might have an auditorium with a pool. That's completely different than a rec center that's all a gymnasium. There's a huge difference in what you're trying to accomplish each one. So there is no ballpark cost estimate. However, we will talk about financing in our next session. So we'll go deep into cost and finding ways to pay for financing. So I will transition to the end here. The next session in 2 weeks, we're going to talk about financing, and Peter touched on some significant ones from the beginning. You can still just buy these things. But one thing I do remember or do want to talk about is the value is that it's an investment, not just a cost. A microgrid is an energy system that produces value. So that value is either going to be used by you or it can be turned into revenue for you. It really just depends on what you're doing and how you're doing it. And then, of course, one of the things that got me excited when I got into this 10 years ago was that a county in Maryland called Montgomery County, Maryland, created a concept called a microgrid as a service and was able to build 12 microgrids and use no capital to do it. So there's a way to do that kind of thing, and we'll talk about that. And it's now called energy as a service. But we'll be going through all those different ways to purchasing things that you want in session 5. Session 6, we'll be putting it all together, and we kind of touched on that as well, looking for designing your systems that are for the modern age and the world that we're living in today, which is new and different, and making sure that you are resilient and robust to be able to handle mission critical responsibilities because you are municipalities if you are building these things. So thank you very much to our speakers. They're awesome. Last time you get to see Amy and Peter, so hopefully we'll have them back with some other series, and we will see you in 2 weeks. And we get to talk about really crazy things like what in the world is going on in the world at session 6. So have a great day. Everyone be well and be safe.
Thank you.